Hello guys, thank you so much for being with me in another artificial neural network tutorial video. The idea is very simple in gradient descent algorithm. Imagine that the cost function is like this. We want to find only the minimum. We start from a random point. The starting point can be anywhere. Suppose our eyes are closed and we are standing at this starting point. Suppose the optimal point is at the zero level and the location of the lake. Let's say we can just rotate 360 degrees and take just one test step and measure which direction we will have the most reduction if we take one step. We do this until we reach a local optimum. That is the point where if we take each step, we will not have any decrease in height. Either we will face an increase in height or there will be no change in the level of the height. This is called gradient descent algorithm. There is nothing new here. We use the scalar function only to calculate the differential of the function in one-dimensional space. But in our discussion, f itself is a number that is a function of w. W is a vector. In one-dimensional space, you have seen this formula for calculating the slope. When f is a non-linear function, you know that this relation calculates the slope of the tangent line to this curve. This h is actually the same step. The smaller this h is, the more accurately this slope represents the slope of the function f at a particular point. Now the difference is that in multidimensional space, instead of taking the differential at one point, we calculate this differential with respect to several parameters that are the elements of a vector. We abbreviate dw here. In fact, the same ratio dl to dw is considered, which is just written dw for simplicity. We want to calculate the differential of the loss function with respect to w1. We have w, so we calculate lw. This will be a number. We calculate the gradients for each of these w's respectively. Pay attention that all other w's are assumed to be fixed and only one of these w's is added with a very small value. Now we calculate the loss function with this new value of w1 and subtract it from the value that we previously calculated for this function with the original values of w. Then we divide the result of subtraction by this small addition value. This is the definition of gradient descent. This gradient has a meaning in mathematics. The gradient is the direction in which our function increases the most. Obviously, when we are looking for the largest reduction, then we must multiply this numerical value by negative sign. You can see the implementation in Python here. What is wrong with this method? This method is highly dependent on h and sometimes not accurate enough. Finally, we have to estimate this value is accurate when h is exactly 0, and in this case we will face one of the mathematical ambiguity states. Therefore, the exact calculation of this gradient is not possible. The second drawback is that this algorithm is very time consuming. For these two reasons, we do not use this numerical method in artificial neural networks. Rather, we use the gradient descent algorithm itself and backpropagation. But sometimes we take help from this numerical analysis method to check the correctness and accuracy of the algorithmic method. This is one of the ways to reduce errors in artificial neural network implementations. This analytical method is much simpler to implement than the backpropagation algorithm, but it also has the mentioned disadvantages. If the results obtained from the two methods were very different from each other, we can be sure that there are some problems in the backpropagation methods. Because the analytical method has no possibility of error, in this way, the correctness of backpropagation can be checked. You are definitely familiar with the backpropagation algorithm from machine learning topics. But as a basic content, here we also provide explanations. The implementation of the gradient descent algorithm itself in a non-analytical way is given in this slide. You have seen the implementation of the analysis. This is also a non-analytical implementation. In the implementation of gradient descent algorithm, what is important is the calculation of weights. This implementation is related to the basic and the simple version. Changes can be made in it. For example, if we want to calculate the loss function, we have to calculate this function on the entire data. These calculations can be very voluminous and time consuming. To solve this problem, we can consider a small part of the training set, and by calculating the loss function on them, estimate the gradient descent. In this contour figure, the blue points represents the small value of the loss function, and the red color represents the large value of the loss function. We calculate the gradient descent at each point and move one step in the opposite direction until we reach the local optimum point. If we are lucky, this local optimum is the right point. This implementation is also related to batch gradient descent, which estimates the gradients. This method has more uses than the original gradient descent version. In conversation, we usually do not consider this method as a mini batch and call it batch. There is a very special mode in which only a specific data is used. There are several reasons for using this method. For example, there is a huge amount of data, or the lack of access to all data at the same time can be reasons for using this method. In some sources, this method is called stochastic gradient descent, but we refer to stochastic gradient descent as mini batch method. The size of these batches is not a hyperparameter because we never use full batch gradient descent. We always have this kind of fluctuation in the graph which has a decreasing trend. With suitable alpha, we should have such shape, such a figure. We don't know how much alpha is suitable, so we start with a random alpha. If alpha is smaller than the appropriate value, the algorithm becomes more time consuming. If alpha is larger than the optimal alpha but not too much large, we initially have improvement, but with more repetitions, improvement is not observed, but it is still better than the case where alpha is much larger than the optimal alpha, in which there is no improvement at all. The new topic that I want to mention here regarding the machine learning course is the topic of updating the weights. This is a very important discussion because these updates may take days, months, and years. Because these updates may take days, months, and years, various methods are introduced in between, such as AutoGrad, ADAM, Momentum. We will compare and review these methods, and none of these methods are superior to others. In some problems, one method is more suitable, and in some other problems, other methods are suitable. Determining the right method requires gaining a practical experience and cannot be taught in any training course. It can only be achieved with a lot of practice. In some sources, it is mentioned that other method is better than other, but this is not the case. None of these optimization methods is preferable to the other. Limiting yourself to one method will keep you away from the optimal answer. Practice and gain experience yourself, and don't look for any shortcuts. Have a nice time.